Alrighty, guys. So I'm going to do a related rates for you. And I just wanted to remind you that related rates uses implicit differentiation and the chain rule. So implicitly defined functions such as, x, y plus 2x plus 3y squared. If you're taking the derivative with respect to x, remember you're going to have those extra y primes hanging around and then you have to isolate. So we'll do practice with the implicit as we do the problems. But essentially, that's the technique you're going to use to help you solve these. And there's two types of related rates problems. There's the classical problems, which we covered in class, right? So inflating, deflating a balloon, an oil slick, so circle problems, heating a circular plate, the sliding ladder problem, distance between two cars moving, rising and falling water levels in a cone, and we did, I believe, winches. And the problems that students find a little more difficult are the moving particles, the shadow problems for sure, and theta problems, so where the angle is changing in relation to some other changing quantity. So I'm going to do a review of the classic ones. I've got your book right here. This is section 4.6 of the best book. And anyway, we'll just do some of these, and I'm probably going to break this into two videos. So that way we'll have the classical examples in one video and then the ones that students deem more difficult in another. And what I want you to remember is you're going to be given some information. So you need to write down what's given. You need to make a sketch, and you have to determine what quantity are they looking for, all right? And when you make your sketch, when you think about your scenario, what you want to do is you want to relate what's going on to some geometric formula. So again, optimization kind of had that tone as well. All right, so let's look at the inflating balloon. We have a balloon that's being inflated at a rate of 10 cubic feet per second. So right away, what I'm going to do is I'm going to write down what is being given. All right, so I know that it's being inflated, right? So it's blowing up. And what that means is that the volume inside that balloon is getting bigger and bigger, and the radius inside that spherical balloon is also getting bigger and bigger. So what I know is that the balloon is being inflated at a rate of 10 pi cubic feet per second. So I know that dv dt, the rate of change of the volume with respect to time, is equal to 10 pi. And that's cubic feet per second. Okay. They want to know at what rate is the radius increasing. So what am I looking for? I want to find the rate at which the radius increases with respect to time when the radius is equal to 2. All right. So I'm given some information. I know I'm dealing with a sphere, right? So, I'm not that good at drawing, but here's a sphere. This is the great circle. So if you cut the sphere in half, right, through the hemisphere or the equator, if you want, you get this circular cross section that has some radius r. So as the balloon's getting bigger, this radius is also increasing. If the balloon was deflating, not only would we make this volume negative because it's decreasing, but the radius would also be decreasing. All right, so these are probably some of the easiest problems are the sphere. The sphere and the circle are probably the easiest ones. Okay, so what I need to do first is I wrote down what was given. I made a quick sketch, all right? And I know what I'm looking for. I want to know at what rate the radius is changing when the radius is 2. So what I have to do is take my picture and relate it to something geometric. Well, I'm thinking of the volume of a sphere, and that's 4/3 pi r cubed. Okay, so that's the geometric formula for the volume of a sphere. Now, once I have the geometric formula, all I have to do is take the derivative, right, and then plug in the information and solve for what I'm looking for. So let's take this derivative. The derivative with respect to time of volume is equal to, now remember, 4/3 times pi, that's some number. So that's a constant multiple. And right here, the derivative of r with respect to time is 3r squared dr dt, right? So remember, we're taking the derivative with respect to time of r cubed, and this variable does not match that variable. And when that happens, you take the derivative just like you would if that were a t, but the difference is you're going to have to multiply the result by dr dt. Okay, so let me make this a little nicer. We have dv dt, right? Derivative with respect to time of v is dv dt. It's equal to 4 pi over 3 times 3r squared dr dt. And this right here is the quantity I'm looking for, right? This is what I'm trying to find right here, dr dt. So I want to clean this up first. I took the derivative and I noticed that these 3's here cancel. So I've got dv dt is equal to 4 pi r squared dr dt. And at this point here, if I want to, I can plug the values in and then isolate dr dt, or I can isolate dr dt first and then plug the values in. I'm going to go ahead and plug in now. Sorry, this thing is like super close, so I'm going blinded by it. So dv dt is 10 pi. That's equal to 4 times pi. Now we want to find dr dt when r is 2, so I'm going to plug a 2 squared dr dt. So we get 10 pi. Now look, I'm going to tell you right now what I normally do, and you don't have to do this. Let me just rewrite the left-hand side the way it is. This would be 4 times pi times 4, or 16 pi dr dt, right? So if I'm going to isolate dr dt, I'm going to divide both sides by 16 pi. What I want you to know is when you have, the same number on opposite sides of an equal sign and they have the same sign, then they cancel. So I just get rid of those right away. So what I end up with is 10 over 16 is equal to dr dt. And then, of course, I probably want to simplify that a little bit. 2 goes into 10, 5. It goes into 16, 8 dr dt. My interpretation, if I'm asked to justify or interpret what that means, now, I got to keep track of my units now, right? Because I was given units, so I have to keep track of my units. So this is the rate at which the radius is increasing, and it's increasing because this is positive, right? Let me write it again over here. dr dt is equal to 5/8. And not only that, but if it's a radius is in terms of linear measure, right? So it's not going to be feet squared or feet cubed. It's just going to be feet. So what I know is that the rate of change of the radius, or the radius, is increasing at a rate of 5/8 feet per second at the instant when r is equal to 2. Okay, and so I'm saying a verbal interpretation. You'd have to write it down in your work, but that would be the interpretation. All right, so that's a sphere problem. So we did an inflating balloon. And again, if this were deflating, suppose it was the same exact problem, but it said the rate of change of the, maybe it says a balloon is being deflated at a rate of 10 pi. I would just do this here, which means I would do this here and this here, right, and this here. So my answer would come out negative, but I wouldn't write in my interpretation that, it's changing at a rate of negative 5/8, let's say. I would say that the radius is decreasing. The negative implies that it's decreasing. So the radius is decreasing at a rate of 5/8 feet per second at the instant, or at the moment when the radius is equal to 2. All right? So very, very simple. Let me change my page. And let me just do something with this camera because it is officially on my last nerve. Okay. So let's see what else we got here. There's nothing good in this book. There isn't. You know what? Let me look something up here really quick. So bear with me a second. I'm looking up in my computer to see. Here's some related rates practice. Let's see what's in this one. I just need some more. Okay. Good. Actually, I'm going to print this. Hit print. Print. That way I don't have to go, because I'm trying to watch what I'm doing on the screen as I'm talking, and I can't do that when my other window's up. Okay, so let me just put this right under here. Okay, sounds like 25 pages are being printed, but let's look at this one. Water is leaking onto a floor, forming a circular pool. So what do we have? We have a circle type problem, right? So I'm going to make a sketch. Here's a circular puddle on the floor caused by the water dripping, okay? The radius of the pool increases at a rate of 4 centimeters per minute. So, as this circle grows in size, the radius is also growing in size, right? So there's a relationship between the area of the circle and the radius of the circle. What I know is that dr dt increases at a rate of 4 centimeters per minute. What I'm looking for is how fast the area of the pool is increasing when the radius is 5. So I'm looking for the rate of change of the area with respect to time when r is equal to 5. So since this is the thing I'm looking for, the area, I have to think to myself, what is the formula geometrically for the area of a circle? Well, we know that area is equal to pi r squared. So I have a geometric formula, I know what I'm looking for, and I know what I'm given, and so I can go from there. Now I'm going to use a blank sheet of paper here just because I need more room. Okay, so we have dr dt is equal to 4. We're looking for dA dt when r is 5, and we know that area of a circle is pi r squared. So again, a really simple type problem. Well, if we know the area, we can find the derivative, right? So the derivative of area with respect to time is equal to 2 pi r dr dt, right? Remember that pi is just a number, so it's a constant multiple. So I'm really just taking the derivative of this piece here. I'm taking the derivative, I'm bringing the 2 down, I'm using the power rule and throwing it in front of pi. You could write it as pi times 2r if you want to. And because we're taking the derivative with respect to time, and this variable is r and not t, then I need to multiply that result, that derivative, by dr dt. Capiche? All right, so this is the thing I'm looking for. Well, that's equal to 2 times pi. Now we want to find this rate of change of the area when r is 5, so I'm going to plug in the 5. And we also know that the rate of change of the radius is 4. So what I'm going to get is dA dt is equal to 20 times 2 is 40 pi. Now again, we're looking for area, and area is in units squared, okay? This thing was in centimeters per minute. So what I can say as an interpretation is I can say the area is increasing at a rate of 40 pi what? Centimeters squared per minute at the moment when r is equal to 5. Capiche? And just to show you, because it was something I had gotten offline, there it is, okay? Another circle problem. Oil is spilling from a ruptured tanker in a circle on the surface of the ocean. The area of the spill increases at a rate of 9 pi meters squared per minute. What do I know? I know that the area, the rate of change of the area with respect to time, is equal to 9 pi. I'll save the units for last. How fast is the radius of the spill increasing? We want to find dr dt when the radius is 10 meters. Okay, well, I'm relating the area of a circle to the radius of a circle, which makes sense. Both are changing, they're both increasing. And the question is, how fast is that radius increasing? So again, it's a circle, so the area is pi r squared. If I take the derivative on the left, I get dA dt. The derivative on the right is 2 pi r dr dt. Now that that derivative is taken, now I can substitute values in. This is 9 pi is equal to 2 times pi times 10 times dr dt. This is the thing I'm looking for, right? So 9 pi is equal to 20 pi dr dt. And now if I divide both sides by 20 pi, that's going to give me, so again, these pi's are going to cancel. I'm going to get 9 over 20 is equal to dr dt. And I can't reduce that any further. So I would just say the radius is increasing at a rate of 9/20 meters per minute at the moment when the radius is 10 meters. Done. All right, let's do a ladder. So let's see here. We did balloons. We did balloons. We did oil slicks or circular things. It could be a circular plate is heating. It could be you throw a rock into a pond and, you've got these concentric circles rippling out. They're all done the same way. The sliding ladder. The sliding ladder is very famous. And it's very easy too, right? So what you have here is you have a ladder that's 25 feet long. So again, I'm taking this out of your book. So this is a different example. A 25 feet long is leaning against a wall. So here's the wall, here's the ground, and here's my ladder, right? And I know my ladder is 25 feet long, and I know that the length of the ladder cannot change. It's not changing. If the foot of the ladder is being pulled away from the bottom, so somebody's grabbing the foot of the ladder and pulling it away from the wall, okay, at a rate of 14 feet per second. So, this is the x direction, so I'm going to say dx dt, right? The rate of change of x with respect to time is equal to 14 feet per second. So I'm making my picture and I'm labeling it. At what rate is the top of the ladder? So we want to find the rate at which the top of the ladder, which would be the y value, dy dt, what rate is the top of the ladder moving down the wall when it is 7 feet above the ground? Oh, this is the y direction. So y is equal to 7. We're looking for dy dt, the rate at which the top is falling. So guess what? What can I relate this to geometrically? This is a right triangle. Pythagorean Theorem. X squared plus y squared is equal to z squared, or c squared, whatever you want to call it. Now, the only two quantities that are changing here is the top of the ladder is falling and the bottom's being pulled away. The length of the ladder is never changing. So the quantity that remains constant, you can plug that in because the derivative of that thing's going to be 0. So that's nice. So I can say, x squared plus y squared is equal to 25 squared. And I wouldn't even bother squaring that out or anything. Just leave it like that. Now, the thing is we have to find x, right? So we have to use the Pythagorean theorem, right? 25 squared, hypotenuse squared minus leg squared is equal to 576. And if we take the square root of that, we get x is 24. So I used my calculator because I didn't want to make an error. Okay, why do I need that? Because once I take the derivative, I'm going to have to plug in x and y's, right? So again, this is implicit differentiation. We're going to take the derivative of the x terms just like we normally would, but we're going to have a dx dt or an x prime. So I'm going to use some prime notation here. Ditto with the y, because y, we're taking derivatives with respect to time, and neither one of those variables is a t. So let's take the derivative. The derivative of this term is 2x prime. Derivative of this term is 2y prime. Derivative of a constant is 0. And to make matters even better, we can get rid of the 2 by dividing through both sides by 2. So what we end up with is x prime plus y prime equals 0. At this point, and only this point, I'm going to look at this thing and say, all right, I'm looking for dy dt, which is the same as y prime. This is the guy I'm trying to solve for. So at this point, I'm going to plug in what I know. I know that x is 24 times x prime, which is 14, plus y, which is 7, times the thing I'm looking for is equal to 0. And remember, with these things, we want to get y prime by itself. So 24 times 14 is 336, right? So, if you want, this is 336 plus 7y prime equals 0. So I'm going to subtract 336 from both sides. And then I'm going to divide by 7. And thankfully, it goes in evenly, and we get negative 48. Now, we don't say the top of the ladder is sliding down the wall at a rate of negative 48, what were the units? At a rate of negative 48 feet per second. No, this indicates that the top of the ladder is falling, right? So how we would interpret this is we would say the top of the ladder is falling at a rate of 48 feet per second at the moment when the top of the ladder is 7 feet above the ground. Capiche? Now let me look in those printouts and see if there's a ladder problem in here. We'll do one more. No ladder problems here. Terrible, terrible, terrible. No ladder problems. I think you guys all, no matter how bad you think you are at calculus, I think you all know how to do ladder problems. Let me see in the book if there's one more. Yes, there is. So this is page 235, and this is number 9. So what we have is a ladder that's 15 feet long, leaning against the wall of a house. So here's the house, here's the ground, here's the ladder, and it's 15 feet long. I know I have a right triangle. That means I'm going to use x squared plus y squared equals z squared, right? Pythagorean Theorem. Okay. The bottom of the ladder is being pulled away from the house at a rate of 4 feet per second. So what do I call this side? This is x. dx dt is equal to 4 feet per second. How fast is the top of the ladder sliding down? So the question is, what am I trying to find? How fast the top is sliding down when the bottom of the ladder is 9 feet from the wall. Okay, so a little bit of a twist because, well, I mean, these variables do not have to match naturally. But we want to be careful. It's not when, the top of the ladder is, 9 feet from the floor. It's when the bottom of the ladder is 9 feet from the wall. So here, x is 9, right? And by Pythagorean theorem, I can do 15 squared minus 9 squared is equal to 144. So that makes y equal to 12 here. So I have my picture. I have a geometric formula. I was given x. I was given dx dt. I found y by using Pythagorean theorem, and I'm looking for dy dt. We're ready to go, right? So let's take a derivative. Oh, before I take a derivative, what I know is that this length of the ladder is never going to change. So I can go ahead and pop that in there for z. So I've got x squared plus y squared is equal to 15 squared. So taking the derivative implicitly of both sides, I'm going to have 2x prime plus 2y prime equals 0, right? And this is pretty, I mean, you guys could just memorize that, right? 2x prime plus 2y. I would write this down for my grader, And then I would do xx prime plus yy prime equals 0. Why? Because the grader will know that you divided through by 2 to get rid of it. Right? Well, x is 9 and x prime is 4 plus y is 12 times y prime is equal to 0. And now I can solve for y prime. I'm going to subtract 36 from both sides. And I'm going to divide both sides by 12. And so we get -3, right? So what this means, if I were to write, so again, I'm just verbalizing it, but you would have to write it. I would have to say that the top of the ladder is falling or sliding down. That represents this negative here, sliding down the wall at a rate of 3 feet per second at the moment when the bottom of the ladder is 9 feet from the wall. So I think you're all with me on that. You did really, really good on ladders when we did study this back in the day. I know it's been a while, but you know, you guys are not stupid. You're smart. So if you have any questions on this, just let me know. All right, so I'm going to check off sliding ladders. Try and make that straight. Ching. Distance between cars. All right. So, you know, a car is going south, another one's moving east, right? This car is going this way, this car is going this way, and they're going. And the distance between them is changing, right? As this car is moving to the east and this one's moving south, this distance gets bigger and bigger and bigger the further apart they get from each other, right? So all three things are changing. This car is changing, and this distance is changing here. But the beautiful thing is when we're dealing with the two-car scenario, we're dealing with a right triangle, and so it's Pythagorean theorem again. So the Pythagorean theorem comes in nice and related rates because we get to use it for changing distances between cars, or if people are walking, we get to use it for the ladder problems and many other problems. So keep that in mind. Okay, so what we're going to have, it says at any given moment. So at any given moment, a car is 30 miles north of an intersection. Always let the intersection be the origin, okay? Make a sketch. This is the intersection. It's the point 0, 0. And at a given moment, there's a car here, which is 30 miles north of this intersection. And it's traveling toward the intersection. So I want to keep track of that. It's heading toward the intersection at a rate of 45 miles an hour. All right, so at the same time, a truck is 40 miles east. So I'll call this the truck here. It's 40 miles east of the intersection. And he's traveling away from the intersection. So he's traveling in this direction, away. This car is getting closer to this truck's going further away. So the distance between them is still going to change, right? He's traveling away at a rate of 35 miles per hour. Is the distance between the vehicles increasing or decreasing at that moment, and at what rate? Okay. Whew, okay, so we want to know, is this distance here going to decrease between them? And again, this is always going to be a right triangle problem. And here's another thing. Sorry, I have, itchy. I have mosquito bites all over me. So this distance here is 40 miles east. So I can say X is 40, okay? Like, I'm not done with my picture yet. And over here, this car is 30 miles north at a given moment. So my Y is equal to 30. So based on that, I have 30 squared plus 40 squared is going to be 50 squared, right? So this is Z. And anyway, this is going to be a 50. 3, 4, 5 triangle. All right. So the geometric formula I'm going to use is x squared plus y squared is equal to z squared. Now the difference is I can't go plug in this 50 in because it's not constant. This is changing, and this is changing. So all three variables are changing. So I can't just, plug a number in and take the derivative and let it equal to 0 anymore. That's the difference between this and, say, a ladder problem. Okay, so the first thing I need to do is, I need to figure out some things. Okay, is the distance between it increasing or decreasing, and at what rate? So let's differentiate this thing here. So I'm going to have 2x prime plus 2y prime is equal to 2z prime. And if I divide through by 2, I get xx prime plus y prime equals z prime. Now I know what my x, my y, and my z is. That's the easy part. The thing I'm looking for, if this side is z, and I'm looking for the rate at which the distance between them is either increasing or decreasing, I'm looking for dz dt or z prime, right? Those mean the same thing. So this is the thing I'm trying to solve for. All right, so we want to find dz dt when x is 40 and y is 30. Now, what about x prime and y prime? I need to know what those are. Well, that's easy. X prime is going to be 35 and y prime is going to be negative 45. And how on earth did I figure that out? Well, distance equals rate times time, right? So this car here is 30 miles north and it's traveling at it's 30 miles north, traveling at 45 miles an hour. Okay, so what I know is dy dt, or y prime, is negative 45. And over here, this truck is 40 miles east of the intersection, and it's traveling at a rate of 35 miles an hour. So dx dt, or x prime, is 35. Now, this is negative because it's headed toward 0, toward the intersection. I'm sorry, I keep tilting my paper. So let's plug stuff in, shall we? We've got 40 times 35 plus 30 times negative 45 is equal to 50 z prime. This is the thing I'm looking for. So at this point, I can go ahead and multiply that out if I want to. And if I do that, I'm going to find some sum here and then divide by 50. So we got 40 times 35, which is 1,400. And then 30 times negative 45 is negative 1350. So I'm just going to change this to a minus 1350. And that's equal to 50 z prime. Now 1,400 minus 1350 is 50. So we have 50 is equal to 50 y prime. So y prime is equal to 1. All right? Or 1 mile per hour to be more precise. So how I can describe this is I can say that at a given moment, or at the given moment, the distance between the vehicles is increasing. How do I know it's increasing? This is positive. If this would have turned out to be a negative number, then I would know that the distance is decreasing. But anyway, this is, sorry, oh, I goofed up. This is z prime. Yikes, I'm sorry. Z prime. So the distance between the cars is increasing at a rate of 1 mile an hour. All right. Let's see if there's another one here in this. Well, there are cones and shadows and thetas, but there's not another distance between two cars. So let's see. Okay, here's a tricky one. This is number 6 from your book. It's not hard, but there's a little trick to it. So once you're aware of it, you'll be okay. And I think we did this one in class. So we have two automobiles that start from point A, which is always going to be my origin. So this is my point A right here. At the same time, one travels west at 80 miles an hour. So this car here is traveling west at 80 miles per hour. And the other one is traveling north. So this other car is traveling north at 45 miles an hour. Okay, so my rates are positive because they're traveling away from the origin or away from each other. All right, and the question is, how fast is the distance between them increasing? So the distance between them is here. Okay, and I'll call that z. You can call it whatever you want. This is x, this is y, this is z. How fast is the distance between them increasing? So I already know that the distance is increasing 3 hours after they start. So that's the little kicker there. We have this little time increment in there. So, all right, this is a rate. So this is x prime. This is a rate. So this is y prime. Now, z, I don't know what that is yet, but what we're looking for is z prime, right? How fast is the distance between them increasing after 3 hours? Well, I have to use that 3 hours to find my x and y, right? To find x, it's just 80 miles per hour times 3 hours, right? And that's 240 miles. So x is 240. And I'm going to do the same thing for y. I'm going to have 45 miles per hour times 3 hours. Those are going to cancel. And so what do we have? We have 15, 12, 135, I think. I better double check because I've been working all day and I am tired. Ooh, 45 times 3. So 135, yeah. Okay, so y is 135. To find z, I just do 240 squared plus 135 squared, and that's a huge number, and take the square root, and it doesn't go in evenly. So z is the square root of this little nightmare, which is 75825. 75825. And I'm looking for z prime. And I'm out of focus. All right, well, what geometric formula we're going to use? We're going to use x squared plus y squared is equal to z squared. Now again, this car is moving, that car is moving, this distance is moving, so everything's in motion, so I can't just plug in numbers until after I take the derivative. Nothing's constant here, okay? So let's take the derivative, and I'm going to multiply through right away. So we're going to have x prime plus y prime equals z prime, right? So that's going to give me 240 times 80 plus 135 times 45 is equal to the square root of 75825 z prime. So z prime is equal to 240 times 80 plus 135 times 45 all over the square root of 75825. And if I put that into my calculator, which I will do, oh my gosh, this thing is so crazy that it's backwards. Let me move my light over a little bit. See if I can get a little more light on that. Not really. So let's see, we've got 240 times 80 plus 135 times 45 equals, I don't know, can you guys see that? Move it over here a little bit more. And then we're going to divide by the square root of 75825. And we get 91.788, right? So z prime is 91.788. So what I could say is that the distance between them is increasing at a rate of 91.788 miles 3 hours after they start. And let me see one other thing here. So bear with me a second. I'm going into my folder. Yeah, and that's it. That's all I wanted to say. I wanted to look up something else. So anyway, sorry that I took that little pause there, but I wanted to prepare something. Okay, so this one has a little bit of a twist because I was given the rate at which they were driving, but I wasn't given the x and the y value, all right, from the origin. So 240 miles and 135 miles. It makes sense that they would be increasing at about 92 miles at the moment when at the moment at 3 hours after the moment they start. All right. I think I put one on AB Classroom, so you can try one of those. So what we have here then, oops, distance between two cars is done. Let's do cones, shall we? Your favorite, the cone problems. All right. So remember that with the cones, you're going to have to use similar right triangles. Oh my gosh, this backward thing is driving me nuts. You guys, I can't deal. We're going to have to use similar right triangles with cones, and we really, really, really need to make that sketch. All right? So, here we go. Water is flowing into a cone-shaped tank. Here's my tank. It's the shape of a cone, right? At the rate of 5 cubic inches per second. What does that mean? It means that the rate at which the volume is increasing is 5 cubic inches per second, right? Water's going in, so the volume's increasing. Now remember, as the liquid's being poured in, you have this liquid surface, right? I don't know, I'm drinking, I don't have a liquid surface, but I'm drinking an iced tea right now. You see I've got that very thin liquid surface, if you forget about the ice. This is a cylinder, so it really is circular, just doesn't look that way. Anyway, it has a radius which we call r, right? Now, the cone itself, the container that's holding the water, also has a radius. Okay, it says the following. If the cone has an altitude or height of 4 inches and a base radius of 3 inches, so this is your base radius, how fast is the water level rising? So, you know, this is some r that we don't know what it is. And this is some depth, or h, right? We call it h, that we don't know what it is. We know the height of the cone, and there's some unknown depth here. So what we're trying to find is how high is the water, or what is the depth of the water when the water is 2 inches deep. Sorry, not what is that? What is the rate of change of the depth of the water when the water is 2 inches deep? Okay, geometrically, I have to remember. Oh my gosh, what is that formula for the volume of a cone? Oh, we remember. It's 1/3 pi r squared high, right? There's the geometric formula for cone. And remember that 1/3 pi, 1/3 times pi, you can write as pi over 3 if you want to. This is just a number. It's a constant multiple. So the things that are changing are the volume, the radius, right? As this liquid surface gets bigger and bigger, the radius is going to increase. And as this thing gets higher and higher, the depth is going to increase. So we've got all three of these variables are changing. The problem is that I'm given dv dt, I'm looking for dh dt, and so what I've got to do is get rid of a variable with this one. Well, with most cones, I got to get rid of it. I have to have two things that are changing. All right, so if I know dv dt and I'm looking for dh dt, it looks like I need to get rid of r, right? I need to get rid of r here. So this is what we do. We make similar triangles. We have, so let me get a couple of colors here, about lavender and lime green. Right? So I have this little triangle, R and H. Right? So that's this one here. It's a right triangle. Right? And then I have the bigger triangle. which is 3, 4, right? This triangle here. This is 3. This from here to here is 4. And this is the hypotenuse of the triangle. So these are right triangles. And I'm going to use similar triangles to help me get rid of r. So what I can say is the following. This radius is to that radius as this height is to that height. Okay, so r is to 3 as h is to 4. And I want to get rid of r, so I want to solve for r. So that means that r is equal to 3 over 4 times h. Okay, so I cannot plug anything. Do not plug with cones anything. Any of the numbers, anything that's known, do not plug that into. Don't even take your derivative until you get rid of a variable, first of all, and then plug stuff in. All right, keep it in mind that way. So what I have to do is I have to take my volume formula and I have to replace the r with 3/4 h. So I have volume is equal to pi over 3 times 3 over 4 h quantity squared times h. Remember, I have to square everything in here, top, bottom, and the variable. So volume is pi over 3 times 9/16 h squared times h. And h squared times h is h cubed. So here's another thing I like to do. Because we have to take a derivative, I like to simplify this. So 3 goes into itself once, and it goes into 9 3 times. So what I'm left with is v is equal to, this is 3 times pi over 16 h cubed. There's my compacted formula, and that's the thing I want to take the derivative of because that's an easy derivative. So let's do it. The derivative on the left is dv dt, or v prime. The derivative on the right, remember this is just a constant multiple, so you leave it there. And what you're doing is you're taking the derivative of this right here. So it's 3h squared dh dt. All right, and now I can combine those numbers together. So I have dv dt is equal to 9 pi over 16h squared dh dt. Now, I'm looking for this. This is what I want to solve for. And I know what this is because they gave it to me. It's 5. So I'm going to plug that in. And I want to find the rate at which the depth or height of the water is changing with respect to time when the depth is 2. So I can go ahead now and plug in my 2 and then solve for dh dt. So this is going to become a 4, all right? And 4 goes into itself once, and it goes into 16 4 times. So I have 5 is equal to 9 pi over 4 dh dt. And now if I multiply both sides by this reciprocal, I'm done. So what I'm going to have is 20 over 9 pi is equal to dh dt. And I cannot simplify that anymore. So how can I interpret that to the greater? What can I write down when they ask me for interpretation? I can say the water level is rising at a rate of 20 over 9 pi inches per second when the water is 2 inches deep. Okay? Okay, so let's look at a cone problem here. Another cone. Okay, so we have a conical paper cup that's 10 centimeters tall. So right away, what I do is I make a drawing. Here's my paper cup. It's a cone, and I know it's 10 centimeters tall. All right, so from this point here all the way to here is 10. Okay, the cup is being filled with water so that the water level rises at a rate of 2 centimeters per second. What does that mean? It means dv dt is equal to 2. At what rate is water being poured into the cup when the water level is 8 centimeters? At what rate is water being poured into the cup when the water level is 8 centimeters? So the question is, what am I looking for? I'm looking for dh dt when h is 8. Oh, and I forgot my radius up here. This is 10. No, that's wrong. I'm sorry. No, I'm going to have to stop this video now and cut that off. Crapola.